On the previous video, we calculated the electric field for this potential by taking negative the gradient of the electric field, and negative the gradient of the potential, and the electric field turned out to be this. And now the question is asking for the charge distribution. So I wrote the electric field here in a suggestive manner. The charge, and the way we're going to find the charge distribution is we know that the divergence of E is equal rho over epsilon, which means rho will equal delta E times epsilon. Now, so I do have to take the divergence of the electric field, but here we have to be careful because this blows up at R equals 0. So we have to manipulate that in such a way that we capture this situation as we calculate the divergence. Okay, and so the way we're going to go about doing this is we're going to do the divergence like that. So this row 0 cancels with this row 0, so we get Q over 4 pi. Okay, and this is going to be the same first, so E minus R over lambda 1 plus R over lambda times the divergence of R over R squared, which we've done in chapter 1. We know what that is, plus R over R squared dotted with the gradient of this minus lambda R minus R over lambda times 1 plus R over lambda. Okay, and we know what this is. This is just the Dirac delta function. So this is 4 pi Dirac delta function in 3D as a function of R. Okay, and so now we get, let me put a bracket here. So we get, so for this part here, let me evaluate this first part. So for the first part, e to the minus R over lambda, 1 plus R over lambda, times this turned out to be e to the minus R over lambda, 1 plus R over lambda, over lambda times 4 pi Dirac delta function cubed. And as you guys remember from chapter 1, this is nothing but we evaluate this and it goes away everywhere except at R equals 0. So at R equals 0, this expression becomes e to the 0 is 1, and we get 4 pi. Which is, sorry, we get, cube root of R. Dirac delta function cube of R. So this is from 188. Okay, and for the rest, now let me take the gradient. So now I will do this part here. So the gradient of e to the minus R over lambda times 1 plus R over lambda. This is equal to the unit vector R d over dr of the expression of e to the minus r over lambda 1 plus r over lambda 1 plus r over lambda. Okay, so let's go ahead and do it. So d over dr, so this becomes r hat. We start writing here. And this is just minus 1 over lambda times 1 plus r over lambda e to the minus r over lambda product rule plus 1 over lambda e to the minus r over lambda. And so this becomes, if we were to FOIL it, we can cross these terms out here, and we have left r hat r over lambda e to the minus r over lambda. And now putting them together, so we have r squared over r hat times this. Oh, sorry, r over r squared. I flipped these. R over r squared dotted with e to the minus r over lambda 1 plus r over lambda will get me, I already have an r here, cross r, this is just 1, and I have the result, so r squared, so I will get 1 over lambda r. So I'm crossing this with this, I mean dotting, 1 over lambda r, 1 over lambda r e to the minus r over lambda. And so now, so this is one result, and that's another. So now my rho as a function of r will be, I've evaluated them separately, so I could just put them together now. Q over 4 pi, let's open bracket, 4 pi 4 pi, that's, and then multiplied by the Dirac delta function coming from here, and so that plus 1 over lambda r e to the minus r over lambda. And so this would be my charge distribution for this electric field. Let me put it in brackets. Okay, and of course I could figure out what the entire charge on this is. So I could say that Q is just the integral of rho d tau over the volume, which is Q over 4 pi. And if I integrate this, so this would be the integral of the Dirac delta function, d tau, times 4 pi. Could leave the 4 pi here, plus 1 over lambda e to the minus r over lambda over r. Yeah, integral. And this is, of course, on dr. Now, the theta and the phi will give me 4 pi, wait, let me just write it here. So this is a triple integral in spherical coordinates. So the contribution from theta and phi, 2 pi from theta, pi from phi. So that's 4 pi. And then we have r squared dr. Okay. And of course, we are integrating from 0 to infinity over all space to figure out what kind of charge we get. Okay, so let's see what this is equal here. We have here the integral from 0 to infinity of e to the minus r over lambda times r dr. Okay, now to evaluate this integral, we could do this by parts. So r is u, and e to the minus r over lambda is dv. So dr is du, and v is e to the minus r over lambda multiplied by minus 1 over lambda. This is v. So this is going to be uv minus integral of v du. So let's continue it here. So 0 to infinity of r e minus r over lambda dr is equal to uv, so minus r over lambda e to the minus r over lambda minus the integral of v du. So this becomes plus 1 over lambda e to the minus r over lambda dr from 0 to infinity. And so this becomes minus r over lambda e to the minus r over lambda plus 1 over lambda, and there's another, so e to the minus r over lambda, and we divide by the chain rule, so we multiply by minus lambda to integrate. This goes away, and we are evaluating this from 0 to infinity, but you could see, let's see here, so if we plug in infinity, this guy goes to 0, the second guy goes to 0, and if we plug in 0, we get 0. Something is not quite right here, because we're not getting 0 on the second term. We get 1 here. 1 second, something isn't quite right. R over lambda. No, there's the dr here too. So uv so this is r. Oh yeah, if we, okay, let's do this slowly. So this is 0 to t, and we will take the limit as t goes to infinity. It's there's a L'Hopital's on the first one, because we get minus r over e to the r lambda. So here we get infinity over infinity, which we have to use L'Hopital's for that. So the second one, we know it goes to 0. So on the first one, we would get minus 1 over, on the 0, it's going to go away because r is 0. So we get minus 1 over lambda e, this is r over lambda. So this is 1 over lambda r over lambda, and we're going to take the limit as r goes to infinity, and this is clearly 0. Okay, the second term, is where we have the problem, because plug in t says infinity and 0, we get 1. Uh, second, looks like there might be some. Oh, okay. Well, let it be. So we got, yeah, we get 1. We don't get 0. It's, oh yeah, because I haven't evaluated the entire integral yet. Yes, yes, yes. I don't have to be getting 0 from here because this guy here is 1. Right, right, right. Okay, so with that, so we get plus the first term, e. So now I'm doing the second piece. So this piece. So this is e to the minus r over lambda times minus 1. Plugging t here. And then we take the limit as t goes to infinity, which makes this 0 minus e to the 0, which is 1. Minus 1. And so now, plug this back in the integral, and indeed, we get 1. Oh, wait, but this is... 1 second here. Lambda. Still something is not right. Oh yeah, 1 over lambda. Oh, we got oh yeah, this is lambda minus lambda e minus r lambda. Yep, this was the issue. So that fixes this to become plus lambda, which makes this here lambda squared. Lambda squared, which makes uv. So this is minus r lambda vdu lambda. Yeah. Okay, so this becomes minus r lambda plus or minus lambda squared e to the minus r over lambda. So the first one we've already done, it's 0. The second one is at infinity it's 0, and at 0 it's minus lambda squared. And I have here lambda. Oh, right. This is lambda squared here. Yeah, because there's a lambda from here and there's a lambda from here. Or, yeah. No, not on this one, on this one. This one, Okay, so yeah, there was a mistake here. Let me just correct it really quick. This was when we multiplied, there is a lambda squared here. This is a lambda squared. So we've got over lambda squared. So this becomes a lambda squared. Okay, so let me go ahead and evaluate now. So Q, so let me use this color. So Q to check, so I should get 0 if this is correct. Come on.